Welcome to today's paper reading. Today's paper is titled, The Landscape of Emerging AI Agent Architectures for Reasoning, Planning, and Tool Calling, a Survey. This paper, published on the AR14 preprint, surveys the advancements in AI agent architectures by Tula, Masterman, and colleagues from NVIDIA, IBM, and Microsoft. This survey paper focuses on the recent advancements in AI agent implementations, particularly their ability to achieve complex goals that require enhanced reasoning, planning, and tool execution capabilities. The primary objectives of this work are to communicate the current capabilities and limitations of existing AI agent implementations, share insights gained from observations of these systems in action, and suggest important considerations for future developments in AI agent design. The paper provides overviews of single-agent and multi-agent architectures, identifies key patterns and divergences in design choices, and evaluates their overall impact on accomplishing a provided goal. Key themes outlined include the selection of an agentic architecture, the impact of leadership on agent systems, agent communication styles, and key phases for planning, execution, and reflection that enable robust AI agent systems. The introduction of ChatGPT has led to a surge in generative AI applications, particularly those using the Retrieval-Augmented Generation (RAG) pattern. As RAG systems become more robust, the focus is shifting towards the next generation of AI applications, which center around agents. These agents, built on foundation models like GPT-4, are capable of more complex interactions and orchestration, including planning, reflection, and tool use. The debate within the community centers on whether single or multi-agent systems are more effective for complex tasks, with single agents excelling in well-defined problems and multi-agent systems benefiting from collaboration and multiple execution paths. Figure 1 provides a visual comparison of single and multi-agent architectures, highlighting their distinct features and capabilities. Single-agent architectures operate autonomously, handling all reasoning, planning, and tool execution tasks without external feedback. In contrast, multi-agent architectures emphasize collaboration, where multiple agents work together, potentially using different language models and tools. The figure categorizes these architectures into vertical, with a clear leader-follower structure, and horizontal, where agents communicate equally without a designated leader. This visualization aids in understanding the structural differences and potential applications of each architecture type. The success of AI agents in solving real-world problems hinges on their ability to reason, plan, and call tools effectively. Reasoning is crucial for making decisions and understanding complex environments. There are 5 major planning approaches that agents use to enhance their task performance. Tool calling is another key aspect, enabling agents to interact with external data sources and APIs, thereby solving complex problems more effectively. Additionally, the choice between single-agent and multi-agent architectures can significantly impact task handling and robustness, with multi-agent systems often excelling in parallel task execution. This section highlights several notable single-agent methods including react, raise, and reflection. These methods are designed to enhance reasoning and tool calling capabilities. Successful goal execution by agents often depends on proper planning and self-correction. For instance, the react method improves trustworthiness by recording the entire thought process. Raise, built on react, adds a memory mechanism enhancing context retention. However, these methods have limitations such as repetitive actions and struggles with complex logic. Reflection, using self-reflection, improves success rates, but is resource-intensive. Figure 2 provides a visual comparison of the react method with other methods, highlighting its effectiveness across various tasks. Key points include the react method's improved performance with a 6% hallucination rate compared to 14% for the chain of thought (COT) method. Additionally, the react method enhances human interoperability and trustworthiness by recording the entire thought process of the model. This figure underscores the advantages of the react method in terms of accuracy and user interaction. Figure 3 provides a visual representation of the raise method, detailing its structure and components. The diagram illustrates the memory update process, which is crucial for the method's functionality. Additionally, it highlights the tool pool and example pool, which are integral to the method's operation. This figure is essential for understanding how the RAISE method integrates various tools and examples to enhance its performance. Figure 4 illustrates the AutoGPT plus P method, which integrates object detection from a scene image with a language model to select appropriate tools for robotic planning. These tools include Plan Tool, Partial Plan Tool, Suggest Alternative Tool, and Explore Tool. The language model generates goals and steps, which are then executed by a classical planner using Planning Domain Definition Language, PDDL. This hybrid approach significantly enhances the planning capabilities of purely language model-based methods, addressing their constrained reasoning abilities. However, the method faces challenges such as variable tool selection accuracy and limited human interaction during plan execution. In this section, we explore key themes and examples of multi-agent architectures. Key themes include the intelligent division of labor, dynamic team reorganization, and effective information sharing. Examples include embodied LLM agents, which demonstrate the impact of a lead agent, Dylan, focusing on complex tasks, and Agentverse, with distinct phases for group planning. Additionally, MetaGPT addresses unproductive chatter through structured outputs and a publish-subscribe mechanism, improving goal execution. Figure 5 illustrates the superior performance of agent teams with a designated leader. Research shows that such teams complete tasks nearly 10% faster than those without a leader. The leader's communication is primarily focused on giving directions, 60%, while the remaining 40% involves feedback. Additionally, a dynamic team structure with rotating leadership provides the best results, achieving the lowest time to task completion and communication cost. Figure 6 illustrates the Agentverse method, which is a multi-agent architecture designed to enhance AI agents' reasoning and problem-solving capabilities. The method is divided into 4 primary stages: recruitment, collaborative decision-making, independent action execution, and evaluation. The recruitment step allows for the addition or removal of agents based on the progress towards the goal, ensuring that the right agents are participating at any given stage of problem-solving. This method is particularly effective for tasks that require clear isolation of responsibilities for tool calling, demonstrating a more dynamic and parallel approach to task management. In discussing the design choices of AI agent architectures, we observe that single-agent patterns are best suited for narrowly defined tasks with well-defined processes, while multi-agent architectures excel in tasks requiring feedback from multiple sources or parallelization. Feedback mechanisms and human oversight are crucial for iterative refinement and aligning agent responses with human expectations, thereby improving reliability. Group dynamics in multi-agent systems, such as message filtering and clear role definitions, are essential to maintain focus and efficiency. Dynamic team composition further enhances performance by ensuring agents are fit for specific tasks. The current research on AI agents faces several limitations, particularly in the areas of evaluation, data contamination, and benchmark scope. Regarding agent evaluation, the use of varying benchmarks and manual scoring methods introduces potential biases and inconsistencies. Data contamination issues arise from the use of static benchmarks that may not accurately reflect the capabilities of evolving language models. Additionally, the scope of many benchmarks is limited to single-iteration tasks, which does not fully capture the capabilities of agents designed for multi-step reasoning and tool use. Future research should focus on developing more robust and dynamic evaluation methods, addressing data contamination, and expanding benchmark scope to better assess real-world applicability and fairness in agent systems. The AI agent implementations discussed in this paper show significant advancements in reasoning, planning, and tool calling. Both single and multi-agent patterns demonstrate the capability to handle complex, multi-step problems. The optimal agent architecture is found to depend on the specific use case, but the best-performing systems typically include techniques such as well-defined prompts, clear leadership, dedicated phases for reasoning and execution, dynamic team structures, and feedback mechanisms. These techniques make the agents more effective across various benchmarks and problem types. However, there are still challenges to address, including the need for comprehensive agent benchmarks, ensuring real-world applicability, and mitigating harmful biases in language models. This survey aims to provide a comprehensive view of the current AI agent landscape and offer insights for future development. Thank you for watching.